Hello viewers, my name is Dr. Ajay, Associate Professor from the Department of ECE, IARE Engineering College, Hyderabad. And today we are going to discuss the topic end-fire array and binomial array, which is related to the course antennas and wave propagation. So today's topic is end-fire array and binomial array. Let us start our session. As we have seen in the earlier sessions that an array, it is a group of elements which is used to increase the directivity. An array, it is a group of elements arranged identical and with equal spacing in order to increase the directivity of the radiation pattern. An array is used. Here there are four different types of arrays. One is a broadside array, end-fire array and a linear array. So these are the three different types of arrays we have seen, and today we are going to discuss about end-fire array. Here, when we can say that an antenna or an array is said to be an end-fire array. Suppose there are n number of elements here. These n number of elements are spaced equally. These n number of elements are equally spaced with some distance here. And here, when the radiation pattern it is coming out from in this direction. That means we are going to identify, or we are going to design the antenna in such a way that the radiation pattern generated from this type of antenna, it is unidirectional. That means the radiation pattern it is going to fire out at this end point only. Hence the name is given as end-fire array. So here an end-fire array, it is nothing but a group of elements which are identical to each other and are having equal spacing between the elements, where the radiation pattern is produced at this end portion of the array. So we need to design an antenna in such a way that the radiation pattern must fire at the end point of the antenna array. So for an array to be an end-fire, that means an end-fire array, there is some conditions to be satisfied to produce the pattern at this end point. That means the phase angle is such that it makes the maximum radiation in the line of the array. That is, theta is equal to 0 degrees or 180 degrees. Or the 0 degrees or 180 degrees. Thus, for an array to be end-fire, there are two conditions. One is psi is equal to 0 and the theta is equal to 0 or 180 degrees. So this is the required condition for the end-fire array to produce the beam of array at this end point. So here we are going to make an arrangement in such a way that we are going to assume psi is equal to 0 and the theta is equal to 0 degrees or 180 degrees. Right? That means all the elements are in this direction around the 0 degrees only, you can see here. So this is 0 degrees, this is 90, and this is 180, and this is 270. And this is 270, and this is 360. So here either 0 degrees or 180 degrees, whenever theta is equal to 0 degrees or 180 degrees, you can see, observe in the graph here that an end-fire array, it fires the radiation beam either at 180 degrees or in the 0 degrees. So according to these conditions, theta is equal to 0 or 180 degrees. As we have seen, the phase angle, it is given by beta d cos theta plus alpha. Psi is the phase angle and alpha is the attenuation constant and beta is the propagation constant and d is the spacing between the elements. You can see here. This we call it as the spacing d here. And alpha can be written as the attenuation angle or attenuation constant, we can say. And beta is known as a propagation constant. It is given by 2 pi by lambda. Beta is equal to 2 pi by lambda. And we know that the phase angle, the relationship between the propagation constant and the phase angle, it is given by psi is equal to beta d cos theta. So this already we have derived in the first expression of a linear array. So based upon the extension of that linear array only, the same concept is being applied for the n-fire array also. So we are going to take the equation from the linear array, that is n number of elements. That means the array with n isotropy point sources of equal amplitude and spacing. Already we have seen the derivation in the earlier videos. That is based upon that equation we have written here psi is equal to beta d cos theta plus alpha. So the n-fire condition here we are going to denote as psi is equal to 0. Psi is equal to 0 and beta d cos theta, theta is equal to 0 degrees plus alpha. So by simplifying this condition, we know that cos 0 is equal to 1. Cos 0 is equal to 1. So as cos theta is equal to 0, 1, you will get here beta d. That means 0 is equal to beta d plus alpha and alpha is equal to minus beta d. So we know that beta is equal to 2 pi by lambda. So minus 2 pi by lambda into d is the required equation, that is path difference. This is the attenuation constant, or we can also call it as a phase angle due to the path difference. So alpha can be also known as attenuation constant. We can also refer it as a phase angle due to the path difference. Phase angle due to the path difference. So we are going to name it as minus 2 pi by lambda into d. This indicates that the phase difference between the source of an n-fire is retarded progressively by the same amount as the spacing between the sources in radians. So you can see from this equation, alpha is equal to minus 2 pi by lambda into d. Alpha is equal to minus 2 pi by lambda into d. See here, you can see here minus this. Here the notation minus indicates that the wave will be decreasing. The wave will be decreasing progressively as the spacing between the sources in the radians. As the spacing between the sources in the radians. For example, if we say if the spacing between the two sources is lambda by 2 or lambda by 4. Suppose if there are 4 elements. Let us example say the distance between these two is lambda by 2. The distance between these two elements is lambda by 2 and the distance between these two elements is lambda by 2. So based upon this equation, if you substitute here minus 2 pi by lambda into d, minus 2 pi by lambda into d. So here d refers to as lambda by 2. D refers to as lambda by 2. If you substitute here minus 2 pi by lambda into d is equal to lambda by 2, lambda and lambda get cancelled and 2 get cancelled. So finally you are getting minus pi. That means the phase shift or the phase angle is going to reduce progressively. The phase shift or the attenuation angle, the phase angle is going to the beam is going to reduce as the length increases, as the length between the spacing of the elements increase. So for example, if spacing between the two sources is lambda by 4, if the spacing between the two sources is lambda by 4, then the phase angle by which the angle source lags behind the source is given by pi by 2 radians. If we substitute here d as pi by 2, if we substitute d as a lambda by 4, you will get as a pi by 2 radians. So see here, you can see here minus 2 pi by lambda minus 2 pi by lambda into lambda by 4. Lambda get cancelled, 2 ones are 2 twos are. So this is equal to minus pi by 2 radians. And the spacing between the two sources is lambda by 2 or lambda by 4, then the phase angle by which the source 2 lags behind source E is given by minus pi by 2 radians. Now let us to draw the radiation pattern of the n-fire array. So we need to determine the direction of pattern maxima, the direction of pattern minima, and also the beam width, and also the half power beam width. So these are the required parameters to draw the radiation pattern of the n-fire array. So we need to know first in which direction the radiation pattern is maximum and in which direction the radiation pattern is minimum. Hence we are going to find out the direction of pattern maxima based upon the expression. We know that sin n psi by 2 is equal to 1 if sin psi by 2 is not equal to 0. So already we have seen from the equation 26, which is maximum, that sin n psi by 2 is equal to 1 if sin psi by 2 is not equal to 0. So according to the trigonometric series, the solution for this equation, that is sin n psi by 2 is equal to 1, it is given by n psi by 2 is equal to plus or minus 2n plus 1 into pi by 2. So n psi by 2 is equal to plus or minus 2n plus 1 into pi by 2. So if we simplify this equation, you will get the phase angle as psi is equal to plus or minus 2n plus 1 by n into pi. So where n represents the number of sources. So n psi by 2 is equal to plus or minus 2n plus 1 by n into multiplied by pi. So for end fire case, we know that alpha is equal to minus beta d. So to produce a pattern at the end fire, to fire the radiation pattern at any end of the array, the condition is alpha is equal to minus beta d and psi is equal to 0. So these are the two conditions to be satisfied for the end fire array. And we know that psi is equal to beta d cos theta max min plus alpha. So we are here there is a suffix known as min, which indicates that as minor lobe maxima. So psi is equal to plus or minus 2n plus 1. So here psi is equal to alpha is equal to minus beta d, and psi is equal to beta d cos theta max min plus alpha plus or minus 2n plus 1 by n into pi. So let us simplify this expression. If we simplify and cross multiply this expression, that is psi is equal to beta d cos theta max min plus alpha. We shall take this alpha is equal, substitute alpha is equal to minus beta d here. If we substitute alpha is minus beta d, you will get beta d cos theta max min minus beta d. That is equal to plus or minus 2n plus 1 by n into pi. On further simplification, beta d, if you take the common from the brackets, you will get beta d into cos theta max minus 1 is equal to plus or minus 1. If you simplify here, beta d into cos theta max minus 1, that is equal to plus or minus 2n plus 1 by n into pi. On further simplification, you can get the angle, maximum angle of direction as cos theta max equal to plus or minus 2n plus 1 by beta nd into pi plus 1. So this is the expression we got, the maximum angle of direction cos theta max is equal to plus or minus 2n plus 1 into pi by beta nd plus 1. And also you can see here, to find out the minor lobe maxima, we can further simplify by substituting the value of n here. By substituting the value of n, cos theta max equal to 2n plus 1 into beta nd plus 1. So if we take the cos function to the right hand side, you will get minor lobe maxima. The minor lobe maxima is equal to cos inverse of 2n plus 1 by beta nd plus 1. If n is equal to 4, that means here n represents the number of elements. That means whenever I am going to design a n fire array, let us assume that the number of elements in the n fire array is n is equal to taken as 4, and the spacing between the elements is taken as lambda by 2, and alpha is taken as minus pi. For example, if n is equal to 4, d is equal to lambda by 2, and alpha is equal to minus pi, if we substitute the values of here, theta max of minor lobe maxima, that means here 1 represents the first minor lobe maxima. The first minor lobe maxima is equal to cos inverse of, is substitute 2 is equal to n is equal to 1. So let us assume n as 1. Let us assume here n is equal to 1 here, plus 1 by beta nd, where beta is equal to 2 pi by lambda, and here n is equal to 4, and d is equal to the spacing lambda by 2 and plus 1. So if you simplify this expression, you will get the value as cos inverse of plus or minus 3 by 4 plus 1. So if you take the LCM, you will get 7 by 4, 7 by 4 comma 1 by 4. You will get as there is a plus or minus. If you simplify here, plus 3 by 4 plus 1, you will get plus 7 by 4. And if you substitute minus 3 by 4 plus 1, you will get 1 by 4. So you are going to get two angles. One is for 7 by 4, the other one is for 1 by 4. Here 7 by 4 does not exist. Only cos inverse 1 by 4 will exist here. So as 1 by 4 exists, we are going to take only the one value, that is cos inverse of 0.25 is equal to 75.5 degrees. So one angle, that is minor lobe maxima, it is in the direction of 75.5 degrees centigrade. 75.5 degrees. That means here 0, if you take 90, if we take 180, if we take 270, 75 means in this direction. So this is known as the first maxima. This is known as the first maxima in the direction of 75.5 degrees. In the direction of 75.5 degrees, the radiation pattern will be maximum. Similarly, if we assume as n is equal to 2, similarly, if we assume the n is equal to 2, in the above expression, if you substitute the same quantities, n is equal to 4, n is equal to 4, and d is equal to lambda by 2, if you substitute, you will get the second lobe maxima. You will get the second lobe maxima. Here, if you want to calculate the second lobe maxima, substitute n is equal to 2, and if you simplify, you will get the value as cos inverse of minus 1 by 4. Cos inverse of minus 1 by 4. Here, plus 5 by 4 plus 1, you will get 1. And the other angle is minus 5 by 4 plus 1. So, one angle is greater than 1, hence cos inverse 5 plus 4 means 9. 9 by 4 will not exist here. Only one angle will exist, that is minus 1 by 4. Hence, we will get cos inverse of minus 0.25 is equal to minus 75.5. Minus 75.5. It means that the radiation pattern, the second lobe maxima, here the first lobe maxima is in the angle of 75.5. And the second lobe maxima is in the direction of minus 75.5 in the opposite direction. So these are known as a two lobe maximum for n is equal to 1 and for n is equal to 2. Let us find out the directions of pattern minima by substituting alpha is equal to minus beta d in the equation 28.1. So we know that beta d cos theta min plus alpha is equal to plus or minus 2n pi by n. So from this equation, again we substitute the same quantities, that is by considering n is equal to 4 and d is equal to lambda by 2 and beta is equal to 2 pi by lambda. Substitute all these things here, you can find out the value of cos theta min. So by substituting the number of elements as 4 and the spacing between the elements as lambda by 2 and beta is equal to 2 pi by lambda, you will get the cos theta min value. You will get the value of cos theta min. So here, if you substitute alpha is equal to minus beta d here, if we substitute alpha is equal to minus beta d here, and we simplify taking by beta d as common, you will get the value of cos theta min. See here, the cos theta min minus 1 is equal to plus or minus 2n pi by beta nd, and further simplification substituting beta is equal to 2 pi by lambda, you will get this expression. You will get this expression. So here, 1 minus cos theta can be written as 1 minus 2 sin square theta min by 2. 1 minus 2 sin square theta min by 2. So, by applying the trigonometric formula, you will get this value. So, cos theta min can be written as cos A is equal to 2 sin square theta by 2. Cos A is equal to 2 sin square theta by 2. So, 1 minus 2 sin square theta min by 2 can be written as here cos theta min value. 1 minus 2 sin square theta min by 2. And this minus 1 is written as it is. And on further simplification, you will get n lambda by nd. So overall, if you further simplification, taking the sin square theta min to the left hand side and the other components, other equations to the right hand side, you will get plus or minus n lambda by nd. So further simplification, you are going to get theta min by 2 is equal to sin inverse of plus or minus square root of n lambda by 2nd. Plus or minus theta min by 2 is equal to sin inverse of plus or minus square root of n lambda by 2nd. So overall, if you simplify the minor lobe minima, you will get theta min is equal to 2 sin inverse of plus or minus root of n lambda by 2nd. So here, the first, in case 1, we have simplified the major lobe maxima. Now here we are going to find out the major lobe minima. The second case is major lobe minima. So here theta min represents the major lobe minima. That means in which direction the minima lobes we are going to achieve. Now the pattern minima can be obtained by substituting the values of n is equal to 1, 2, 3. For example, let us denote the conditions, satisfy the conditions. N is equal to 4, d is equal to lambda by 2 and n is equal to 1. This is case 1. So in the case 1, let us substitute n is equal to 1. That means n is equal to 1 represents the first minor lobe maxima. First minor lobe maxima. If you substitute here, capital N is equal to 1, and if you apply the sine function and the root for these terms, we know that N is equal to 4 and D is equal to lambda by 2, the spacing between the elements. If you simplify, you will get the value as plus or minus 60 degrees. You will get the values as plus or minus 60 degrees. So it means that the minor lobe maxima are in the direction of 60 degrees. So this is 0 degrees, this is 90, this is 180, and this is 270 degrees. So here 0 and this is 60 degrees. So that means in this direction plus or minus 60 degrees we are getting the minor lobe maxima. Minor lobe maxima. So we know that any radiation pattern contains two types of lobes. Any radiation pattern contains two types of lobes. One is the major lobe. The other one is the minor lobe. These are known as major lobe. So this is major lobe maxima, and these are known as minor lobe. These are minor lobes. So now we have determined the minor lobe maxima. That means the minor lobe maxima, these are known as minor lobe maxima. These are at angles of 60 degrees, and this is at the angle of minus 60 degrees. And in the previous case, we have determined the values as minus 75 and plus 75. These are known as major lobe maxima. So you can see here minus 75.5 degrees, and also you can see here 75.5 degrees. These are known as a major lobe maxima. That means the radiation pattern will appear in this direction, 75 degrees, and here 75 degrees. This is 75 degrees. Let us take second case, that is the minor lobe maxima, by considering the value of n is equal to 2. By considering the value as n is equal to 2. If you substitute the value as n is equal to 2 here, so this is n is equal to 2 and this is n is equal to 3, where capital N is equal to 2 and capital N is equal to 3 represents the minor lobe maxima second one and minor lobe maxima third one. So we'll get two different angles, one is plus 90 and minus 90. That means in the direction of 90 and minus 90 we are going to get the minor lobe maxima. That means you can see here these are known as minor lobe maxima. And if you substitute n is equal to capital 3 here, you will get the value as plus or minus 180 degrees. It means that the minor lobe maxima are also in this direction. That means in this direction and in this direction. So plus 180 and minus 180 and plus 90 and minus 90. And also the major lobe maxima are in this direction. These are known as major lobe direction. That means in the direction of plus 75 and in the direction of minus 75. So this is how to draw the radiation pattern of the N-fire array by calculating all the values of major lobe maxima and minor lobe maxima. By considering the values as n is equal to 1, n is equal to 2, n is equal to 3, you will get different types of lobes in which directions. So this is the final thing. This is the final radiation pattern we are going to get. Thus the minima are situated in the direction of plus 60, plus 90, plus 120. You can see here these are known as minor lobe maxima. And the major lobe maxima are in the direction of theta is equal to 0 and theta is equal to 180 degrees. So based upon the data we got through the mathematical analysis, all those angles are included in the diagram. Plus 60 and minus 60, plus 75 and minus 75, and 0 and 180 degrees. Let us further calculate the beam width of the N-fire array. So beam width is nothing but 2 into angle between the first nulls and the maximum of the major lobes. So beam width of major lobes, here the complementary angle, let us take as gamma. We are going to consider gamma as a complementary angle. So generally, beam width is taken as, if this is the radiation pattern, half of the power of the major lobe. Half of the power of the major lobe, and this angle we call it as a beam width. Half of the power of the major lobe is known as the beam width. Or we can also in another way consider as 2 into angle between the first nulls. 2 into angle between the first nulls. That means if this is the radiation pattern, this is the first null, this is first null, and this is the first null, and this angle to angle between the first nulls and the maximum of the major lobe. That means angle between, this is the maximum of the major lobe and this is this angle. So this angle we can also refer it as gamma. This angle we can also refer it as a gamma. That means 2 times the angle between the first null and the maximum of the major lobe. So this is the maximum of the major lobe. This is the maximum of the major lobe. So again you can see in the figure here. So this is the radiation pattern here, and this is the first null, and this indicates the maximum of the major lobe, and this is the first null, and the angle taken between these two. The angle taken between these two is considered as gamma, and the angle taken between these two is considered as a gamma. So let us, for our mathematical simplification, we have considered as gamma. Beam width is given by 2 into theta 1. From equation 38, we know that theta min is equal to 2 into sine inverse of plus or minus square root of n lambda by 2 nd. Square root of n lambda by 2 nd. On further simplification, sin theta min is approximately equal to theta min. It is equal to 2 into plus or minus square root of n lambda by 2 nd. And we can also further simplification take this 2 into inside, you will get 4 n lambda by 2 nd. So on further simplification, the mathematical simplification, you will get theta min is equal to plus or minus square root of 2 n lambda by nd. Square root of 2 n lambda by nd. So here, the equation 39, from the equation 39, if the array is of length is capital L, that means here suppose n number of elements, there are 4 number of elements are there. And this distance we call it as L. This distance we call it as L here. The length of the array. The length of the array depends upon the number of elements and the spacing between the elements. The length of the array depends upon 2 factors. One is the number of elements in the array and also the spacing between the elements, which is given by the equation L is equal to n minus 1 into D. So which is given by the equation L equal to n minus 1 into D. So here you can see here, we can also equate this L is equal to ND as if n is far greater than D. If n is far greater than D, you can also consider as L is equal to ND. And we know that theta min is equal to plus or minus root of 2 n lambda by ND and plus or minus 2 n lambda by L. So because L is equal to ND, L is equal to ND. And we know that the beam width between the first nulls is given by 2 into theta min. Beam width between the first nulls is equal to 2 into plus or minus theta min value is plus or minus 2 n lambda by ND. So on further simplification, you will get the final value between beam width between the first nulls is equal to plus or minus 2 into square root of 2 n lambda by nd. 2 n lambda by nd. So this is the beam width between the first nulls. And between the first null, if you want to consider the first null, theta 1, the first null as theta 1, then 2 theta 1 is equal to 2 into square root of 2n by L by lambda. So further simplification, we know that nd is equal to L. Substitute here nd is equal to L and bring this lambda to denominator. You will get L by lambda. You will get the value as L by lambda in the denominator. That L by lambda value is indicated as here in the denominator as 2n by L by lambda. So if n is equal to 1, you will get 2 by L by lambda. If you substitute n is equal to 1, you will get 2 by L by lambda. That means the beam width between the first null is taken as n is equal to 1. So between the first null and the major lobe, the beam width is given as plus or minus 2 into root of 2 by L by lambda. So if you in terms of degrees, if you want to represent here, you can represent as in terms of degree by multiplying with 57.3. 57.3, that means plus or minus 57.3 into 2 into square root of 2 by L by lambda degrees. So this is the final beam width between the first null's equation. So if you multiply here, these two here, 2 into 57.3, you will get 114.6 into square root of 2 by L by lambda. So beam width between the first null is given by plus or minus 114.6 into square root of 2 by L by lambda. So this is about the end fire array. Let us come to the topic, the binomial array. So here, why we are going for binomial array? What is the reason behind it? Here, whenever we are going to design any antenna, we observe that in any radiation pattern, there are many number of minor lobes. So our main objective is to reduce the number of minor lobes. So already we have a method to reduce the minor lobes by the method of pattern multiplication. So in another method, we are going to achieve by the method of binomial array also. We are going to reduce the number of minor lobes. So here, if we consider the n of isotropic sources of equal amplitude, but arrays of non-uniform amplitudes are possible, and binomial array is one of them. So the amplitudes of the radiating sources are arranged according to the coefficients of successive terms of the following binomial series, and hence the name is given as the binomial array. So here, whenever we're going to design an array, we see different types of minor lobes. Our main objective is to reduce the number of minor lobes. So if we want to reduce the number of minor lobes, so we need to satisfy the binomial array expression. We know that the binomial series expansion is given by a plus b whole power n minus 1, that equal to a power n minus 1 plus n minus 1 by 1 factorial into a power n minus 2 into b, plus n minus 1 into n minus 2 by 2 factorial into a power n minus 3 into b square, plus n minus 1 into n minus 2 into n minus 3 by 3 factorial into a power n minus 4 into b cube. So this is known as the binomial series expression. So based upon this binomial series expression, so we need to apply the amplitude. So we need to apply the amplitude or the current supplied to each of the elements of the array. So this was first proposed by John Stone in 1929. That is, if the secondary or side lobes in the linear broadside arrays to be eliminated totally, then the radiating sources must have current amplitudes proportional to the coefficients of above binomial series. That means if this is the major lobe and these are minor lobes, to eliminate these minor lobes, so what we need to do is the current amplitudes. That means here 1, 2, 3 and 4 here. 1, 2, 3 and 4. These are known as elements, and these elements amplitude must be proportional to the coefficients of the binomial series. So if we satisfy all the elements according to the binomial series expression, then totally all the secondary lobes will be eliminated. That means all the secondary lobes will be eliminated. We satisfy the elements current with respect to the binomial series equation, and hence only the principal or the major lobe will be we can see the radiation pattern of only the major lobe, avoiding all the minor lobes completely. So in order to satisfy the binomial array, we need to satisfy these three conditions. That is, the spacing between two consecutive radiating sources does not exceed lambda by 2. That means between two sources, not more than lambda by 2 spacing must be exist. The current amplitudes in the radiating sources are proportional to the coefficients of the successive terms of the binomial series. That means if this is the binomial series, we know that 1 and these are 1 and this is 1, 2, 1 plus 1, 1, 2, 1, 1. So this is known as binomial series, and this is applied as for n is equal to 1 element, and there if n is equal to 2, we need to apply the amplitudes according to the proportion as 1 and 1, and if n is equal to 3, if there are 3 elements, suppose there are 3 elements like this, we need to apply the amplitude as 1, 2 and 1. That means the first element is given the amplitude of 1 ampere, and second element is given the current of 2 amperes, and the third element is given the current of 1 ampere. Similarly, if there are only 2 elements, number of elements are 2, then the currents must be 1 and 1. Suppose if we have 4 elements, that means here 1, if n is equal to 4, you will get 1, 3, 3 and 1. That means if there are 4 elements like this, so what we need to do is, we need to apply the binomial series current. That means 1, 3, 3, 1. So 1 amps current, 3 amps current, 3 amps current and 1 amps current. That means all the nodes, all the elements of the array, the currents must be supplied according to the binomial series expansion. So these are the two conditions. These two conditions are necessary to satisfy the binomial array, and the coefficient which responds to the amplitudes of the sources are obtained by putting 1 is equal to 2, 3, 4, 5, 6, 7, 8, 9, 10 in the above expression. See, if this is in this expression, if you substitute n is equal to 1, this is the main binomial series expression. If you substitute n is equal to 1, n is equal to 2 and n is equal to 3, So you will get here number of sources is equal to n is equal to 1, you will get the relative amplitude as 1. If n is equal to 2, you will get 1, 1. If n is equal to 3, you will get 1, 2 and 1. If n is equal to 4, you will get 1, 3, 3 and 1. So like this, you can satisfy the binomial series by substituting the value of n is equal to 1, 2, 3 and 4 up to 10. So we can also simplify, we can also say this as a Pascal's triangle. So by substituting the value of n is equal to 1, we call it as a Pascal's triangle here. See here, this indicates n is equal to 1, this indicates n is equal to 2, this indicates n is equal to 3. So this indicates n is equal to 4. So in the binomial array, we know that the electric field strength in for any type of array is given by 2 E naught cos I by 2. And E norm, the normalized electric field strength is given by cos of pi by 2 cos theta. And where 2 E naught is equal to 1, let us assume as 2 E naught is equal to 1, the amplitude as 1. If we assume this 2 E naught is equal to 1, you will get cos of pi by 2 cos theta, where psi is equal to pi by 2. So if you substitute d is equal to lambda by 2, 2 E naught is equal to 1. From this equation, the normalized electric field strength is given by cos of pi by 2 cos theta. So if another identical array of 2 point sources is superimposed on above array, you will get as generally another element is taken as, then the normalized electric field strength is given as cos square pi by 2 cos theta. And the far field pattern for n sources, the far field pattern of n sources is given by, according to this equation, cos power n minus 1 into pi by 2 cos theta. Cos power n minus 1 into pi by 2 cos theta. So these are the general equations of the binomial array, depending upon the length of the binomial array. So length is taken as the L is equal to n minus 1 into lambda by 2. The half power beamwidth is taken as the equation for the half to calculate the half power beamwidth for a binomial is given by 1.06 by root of n minus 1, where m represents the number of elements, or simply we can also modify it as 1.75 by root of L by lambda. Under D, the directivity is given as 1.77 into square root of n, and the axial factor is given by 1 plus z whole power n minus 1, where z is equal to e power jc. Where z is equal to e power jc. So these are the general expressions for the binomial array to calculate the half power beamwidth, the directivity, the axial factor, the directivity. So these are the things of to design a binomial array. So apart from the advantages, also we are having some two disadvantages of the binomial array. The half power beamwidth increases and hence the directivity decreases. So the half power beamwidth is increased, then the directivity will decrease. So for designing for a large array, larger amplitude ratio of sources is required. That means whenever we are going to design with elements of n is equal to 16 or n is equal to 20, the 20 elements in an array, so it's difficult for us to give larger amplitude for each of the element. That means we need to give different types of currents for different elements. So whenever we are going to design a larger array, so larger amplitude is not possible. Larger amplitude of sources is not possible for us to design. It is also very complex to carry for a person to carry from longer location. That means a binomial array, if n is equal to 20 or 30 elements are there, you cannot easily carry for longer distance communication. So this is about the binomial array. So the main advantage of the binomial array is we can completely eliminate the major lobes. That means here, if this is the major lobe, these are minor lobes. These minor lobes can be completely eliminated. These minor lobes can be completely eliminated by the phenomenon of binomial series expansion. So with this, we close the session today. So this is the end of the two concepts. There is an end-fire array and the binomial array. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.